Okay, perhaps the most important property or the behavior of a sequence is its convergence behavior. That is, we define the convergence or divergence of a sequence by the following limit. Okay, look. Here is, let's say, convergence of a sequence. Okay, first of all, we define the limit of a sequence. So let us consider the sequence AN. If the limit when n goes to infinity AN exists, say L, okay? We say that the sequence AN converges to the limit L. Please be careful. Here, L is a real number. L represents a real number. Okay? A real number, not infinity. Please be careful. Sometimes we write this, recall that. Sometimes we write this, limit f of x when x goes to infinity. Let's say f of x is the function x squared. Remember from calculus 1 that sometimes we write infinity for this limit. So at first sight, it seems that L is infinity, but infinity is not an acceptable limit value. So we do not mean that this function x squared has a limit. Actually, limit does not exist. You know, this abbreviation does not exist. Okay? Does not exist. But of course, writing infinity gives us an information that the function values increases or grows faster than any real number as x increases. So it gives us the behavior of the function x squared for very large values of the argument x. Okay? On the other hand, writing just does not exist doesn't give any information at all, right? So this has a meaning, but in any case, it doesn't mean that there exists a limit. So please be careful. It is similarly limit when n goes to infinity AN. Writing this doesn't mean that there exists a limit. Again, limit does not exist for a sequence as well. Okay. So this behavior to limit converges to the limit L. Otherwise, so I mean, if the limit fails to exist or infinity, okay, then otherwise we say that the sequence AN is divergent. Okay, so it is better to give the formal definition of the limit of a sequence. Look, we say that the sequence AN is convergent, right? So it means that the limit of the general term as n goes to infinity exists. Okay? The sequence an is convergent with limit L, so explicitly written limit when n goes to infinity an is L. Okay? That is the case. If for every given positive number epsilon, okay, there exists an index, say big N integer, of course, depending on epsilon we choose, okay, such that the difference between an and the number, what we call it the limit of the sequence, okay? So that is L minus an is the same, remains smaller than epsilon, okay, whenever the index n is beyond this specified, this integer, this index denoted by capital N. Okay, this is the formal definition, and in practice, this has a meaning that in practice, saying that limit an is L means this: an is approximately L, okay, for n larger than big N. Okay, so this means that an plus 1, if n is sufficiently large, of course. When we choose a sufficiently large index, capital N, it means that the sequence contains elements which are almost L. Or nearly L. Okay? If n is larger than this n. Or there exists big N so that this is true. Okay? So this difference, that is an minus L, this difference can be made as small as we please if n is larger than an index big N. Okay? And in practice, this means that the sequence has elements in its tail, okay? That is, elements with a sufficiently large index are called elements of the sequence in its tail, are all nearly L, okay? That is the meaning of the existence of the limit in practice. Okay, so another important remark is this. Look, we talk about the generating function of a sequence. That is, in some cases, it is possible to find a continuous function with domain x larger than 1, where the entries of the sequence are the specific points, isolated points on the graph of that continuous function. So in that case, look, we can consider the concept of the limit, the concept of the limit of a sequence an okay, is a special case of the concept of the limit, is a special case of the concept of the limit of a function f of x, okay, as x goes to infinity. In other words, if, that is, let f of x be a generating function for the sequence, for the elements of the sequence. In this case, if the limit of the generating function L, that is, exists, not infinity, if the limit of the generating function as x goes to infinity exists, and of course a n is, okay, what is the meaning of f of x to be a generating function? It means that f of x, when x is restricted to n, okay, is a n, that is f of n. So f of x is a generating function. If this limit of the function as x goes to infinity, which is familiar to us from calculus 1, exists, then the limit of the sequence a n when n goes to infinity is also L. That is, limit n goes to infinity a n is L. Right? So if the generating function is at hand, if you find the generating function, so to find the limit of a sequence is trivial, or you may use the techniques you learn in calculating the limit in calculus 1, that is in course math 119. But you have to be careful, okay? So warning in this case, warning. This is a one-sided implication. Look, if the generating function f of x has a limit as x goes to infinity, the same number L stands for the limit of the sequence. But the converse of this statement may not be true. That is, if the limit of the generating function fails to exist, still the limit of the sequence exists, may exist. Okay? So look, please be careful. The converse, or that is, when limit f of x does not exist or fails to exist, it may be the case that the sequence an has a limit. Okay? So please be careful. If the generating function has a limit, no problem. then the same number is the limit of the sequence. But if the generating function has no limit, this means that the sequence may have a limit or a limit fails to exist. Okay? So this does not mean that the sequence has necessarily no limit. Okay? Here is a counter example. Look. There is a very typical example here. Look, the sequence, consider the sequence with sequence AN, where this is a typical example to understand this remark, where AN is sin n pi. Okay? So, of course, n is 1, 2, and so on. So, what about the sequence explicitly? This sequence has all 0 elements. Isn't it? Look, actually, AN, that is sin pi n. What is sin pi? 0. What is sin 2 pi? 0. So that, what is the limit when n goes to infinity? So that limit AN when n goes to infinity is obviously 0. Yes? But, however, on the other hand, if you consider the generating function sin pi x, of course, this is a generating function. With this, AN is clearly f of n. Okay, look. So this is a generating function. If x is restricted to an integer, we get that. If you consider this, observe that limit f of x when x goes to infinity, that is limit sin pi x. What is this limit? X goes to infinity, sin infinity. Okay? So this is a number oscillating between -1 and 1. Okay? It has, this limit does not exist. Although this limit does not exist. Okay? Sin infinity. Maybe any number between -1 and 1. Okay? So although the generating function has no limit when x goes to infinity, okay, the sequence, the corresponding or the counterpart sequence, has a limit, has an obvious limit. Okay? So look, if the generating function has no limit, this means that the sequence may still have a limit. Okay? Please be careful. But if the generating function has a limit, then the sequence has the same limit. So we have no problem. Okay. So please be careful. You can use the limit rules are true. The known limit rules are valid for finding the limit of a sequence. Okay? However, you should be careful in using the Hospital rule, because Hospital rule requires taking the derivative, but an, you shouldn't take the derivative of an with respect to n. Okay? This is just isolated numbers in the plane, not a continuous function, which is differentiable. Okay? So you shouldn't use the Hospital rule, for example. But the other rules should be used. And you can use the Hospital rule for the generating function, if there is any. Okay? And finding a limit for the generating function, then you can find the limit of the sequence, okay, without any trouble. Okay. Let's give, please be careful for, let us give an example for that. Look, show that, or find the limit of the sequence where an is ln n over n. Okay? If it exists. Okay, so use the generating function. Using the generating function, ln x over x. Now, you can use the Hospital rule without any trouble. Consider the limit of the function when x goes to infinity. So obviously we have infinity over infinity type indeterminate form. So by Hospital rule, please be careful. I use the Hospital rule for the generating function. Okay? Actually, look, this is a generating function because f of x, when x is restricted to an integer, positive integer, is a n, isn't it? Choose x as n, we have ln n over n. Good? So by Hospital rule, we have this limit, x goes to infinity, 1 over x, 1, and this is 0. Okay? So that since the generating function has a limit when x goes to infinity, limit ln n over n when n goes to infinity is also 0. So it exists. Okay? So using a Hospital rule in finding the limit of a sequence, you should be careful. Obviously, you have to choose the generating function for that. And look, I will give a list of some limits which appear frequently in this lecture. Limits that appears frequently. Okay, first, this one. We have just proved that in the last example. Ln n over n is 0. Okay, we have just proved it using the generating function and the Hospital rule. Second, limit nth root of n, or this one, limit n to power 1 over n when n goes to infinity, when n goes to infinity is 1. Okay? Do you remember how do we calculate this limit? Please be careful. Pass to the generating function. So consider f of x, which is x to power 1 over x. Good. So how can we find this limit? Remember that this is the case. F of x may be written as e to the power ln f of x. Correct? So when f is positive, so here x is start with n1, so it is positive. Therefore, to find the limit, sometimes use to find the limit of f of x as x goes to infinity here, you can find the limit as x goes to infinity e to the power. So we choose this e to the power ln x to the power 1 over x. So we have a limit x goes to infinity e to the power 1 over x ln x. Good. And remember the continuous function theorem for the limit. Because exponential function is continuous, you can write this one. This limit is e to the power limit when x goes to infinity ln x over x. Why this is true? Because exponential function is continuous. So this rule is very well known. You should first take the limit of the argument for a continuous function and then evaluate the function. Okay? And we have just find that limit ln x over x, okay, is 0. Therefore, we have e to the power 0. Okay? From previous example, this is very well known. So we get that. Okay? So these are actually frequently used limits, and for some fixed x, look, please be careful. We have another limit which is frequently used. N goes to infinity, x to power 1 over n. Please be careful. X is any fixed number in this limit. And the result is always 1 for x positive. Okay? You can prove this. And for limit when n goes to infinity, x to power n. Here is an example for that. Look, let x is 2. Okay? Which must be fixed. So we are interested in this limit. N goes to infinity, 2, 1 over n. And again, using the continuous function theorem, because exponential functions are continuous, 2 to power x as a function is continuous. Take the limit of the argument. 1 over n has an obvious limit 0. Okay? When n goes to infinity. So we have 2 to power 0, and the result is 1. But this is true when x is positive. When x is negative, look, this is not correct. Okay? X to power n is this limit exists and it is 0 provided that x is bounded by 1. So when x is between -1 and 1, this limit x to power n is always 0. But otherwise, if x, the fixed number x, is larger than 1, absolutely, then the limit does not exist. Okay? So you can use this you can prove it very easily. For example, let x is 2, or x is 1/2, which is smaller than 1. Okay? Limit 1/2 to the power n, n goes to infinity. Good. Becomes this one, using the limit rules, 1 over limit 2 to power n. Okay? N goes to infinity. 2 to power n goes to 0. Sorry. Let's see that. Okay. So using the same, 2 to power n is obviously has no limit, or it goes to infinity. So we have 1 over infinity, which is 0. Okay. But if x is larger than 1, okay, for example, 2 to power n, limit does not exist, it is infinity. And another important limit, this one, which is the definition of exponential function. In fact, you are familiar to this one as well. 1 plus x over n to the power n. Look, x is any real number. This limit is always e to power x for all x real. Good. This is the definition of exponential function. Actually, for example, look, limit n goes to infinity, 1 plus 1 over 2n to the power n, okay, which frequently appears. It is e to the power 1/2, okay, where x is 1/2, or the square root of e. Good. And 6 as another important limit which appears frequently, and the formulas in 3, 4, 5, and 6 are true for some fixed x, as you see. X to power n over n factorial. This is always 0 for any real number x. For any real number, okay, n factorial grows faster than nth power of any number x. So this ratio goes to 0 in the limit. It is possible to prove this as well.